Welcome. This question says a coil of wire consists of 6 turns. The strength of the magnetic field that passes through the coil is 4 Tesla. The coil has an area of 2 square meters. The angle between the magnetic field vector and the coil area vector changes from 22 to 55 degrees in 8 seconds. Everything else is unchanged. What is the magnitude of the EMF that is induced in the coil? So let's visualize. I'm actually going to visualize slightly differently this time. I'm going to draw the coil from above. And let me see if I can do this. Yeah. Okay. So there's the coil as viewed from above. Here's all the windings like that. And I'm going to say my N is equal to 6 turns. And we have a magnetic field passing through the coil. I'm going to put my magnetic field through the coil like that. B. So my B is equal to 4 Tesla. And then the area is 2 square meters. And I'm going to show the area vector. The area vector is a vector that's it's defined. And it's defined as having the magnitude equal to the area of the coil in square meters, and a direction which is perpendicular to the plane of the coil. And there's two possibilities. One's going out this way and one's going out that way. And we use a right-hand corkscrew rule, where our fingers represent the current flowing through the coil, curling around the coil, and our thumb then points in the direction of the area vector. However you visualize it, I'm defining that as my area vector. And that area vector, that area magnitude is equal to 2 square meters. And then now I have my angle. There's my angle between the magnetic field vector and the coil area vector. So my initial angle is equal to only 22 degrees, and then my final angle is equal to 55 degrees, and that takes a time of 8 seconds to achieve. So what's going to happen is this thing is going to rotate on an axis, and at some later time we're going to have the coil is going to be in that direction, and my area vector is going to be like that, and there's going to be my new angle. So I'm rotating this, and from a practical point of view, it's much easier to rotate a coil in a magnetic field than it is to change its area or to change the magnetic field strength. This is the easy thing to do. You just put a coil inside a constant magnetic field and spin it, and you will induce an EMF. So speaking of which, what is the relationship between all these things and the EMF? We say, well, EMF is equal to minus N, that's the number of turns, d phi B by dt, but we're not given direct information about the flux. We're given, remember, the flux is like the number of field arrows. It's the number of B arrows passing through our coil. It's an imaginary thing. It's a visualization. But I do know that my flux is equal to the strength of my magnetic field times the area that perpendicular, well, the magnetic field vector times my area vector dotted together. And this equals my strength of my magnetic field. So that's going to be my B times the size of my area times the cosine of the angle between them. So it's the strength of this magnetic field, and it's the size of that area multiplied by the cosine of the angle between. That's the dot product. So if I substitute in, I can say E is equal to minus N, and then I'm just going to say d by dt of BA cosine theta. Okay, so let's do some manipulations here. So E is equal to minus n. We're not changing B, so let's bring that out. We're not changing A, so let's bring that out. So I have d by dt of cosine of the angle. So this equals minus n b a, if you like, delta cosine of the angle over delta t. So my EMF is equal to minus n b a times cosine theta final minus cosine theta initial over delta t. And now I can put some numbers in. So I'm going to say my EMF is equal to minus n is 6, b is 4, a is 2 times the cosine of 55 minus the cosine of 22 over 8. And just a word of caution here. It's not the cosine of 55 minus 22. It's not the angle. It's not d theta by dt. It's d cos theta by dt. And cos theta, cos 55 minus cos 22 is not cos 33. Okay, so we've got to do this step by step. So I'll check them on degrees, and I go cosine 55, enter. And then I'm going to subtract from that cosine 22, enter. And then I'm going to divide that by 8. And then I'm going to multiply that by 2, enter. And I'm going to multiply that by 4, enter. I'm going to multiply that by 6, enter. And I break it up like that because at some point I got sick of losing points because of calculation problems. So I'm very stepwise in my calculations. Now, the answer to that is minus 2.12. I got that minus sign in front. So I'm going to say, I want to rewrite this, because I like to have all my steps kind of visual, available to me when I check. So I'm going to go minus 2.12 volts. So my EMF is going to equal minus and minus make plus 2.12 volts. And so the magnitude of my EMF is going to equal just 2.12 volts. And just, you know, a little bit of maybe subtle points that I've got into the habit of, and that is when it's a magnitude, I don't put a sign there because, you know, a magnitude is just the numerical value, and it's, you know, it's positive. That positive sign here is not the same thing. That means a certain direction of my EMF as opposed to my negative value for my EMF. So that's got meaning. That's not just the absence of a sign. That is a sign. It happens to be positive. And remember that these signs will eventually, they'll tell us which direction the current flows around this coil, and it'll keep track of that when I'm doing more complicated systems. So there we have it.